Welcome to Intermediate Algebra, where we're going to be talking about an introduction to relations. In previous editions of Julie Miller's book that I used to use, this topic was covered in Chapter 3, Section 1, and in a different edition, it is actually Chapter 2, Section 5. So while these notes at the very top right corner, you'll see, say, 3.1, be aware that that number might change depending on which edition of the book you're using. But without further ado, let's have a look at an introduction to relations. But for starters, let's define what a relation is. A relation is defined as a set of ordered pairs, usually expressed where the first element corresponds to x values and the second element corresponds to a group of y values. And as we see in this second yellow box here, the set of the first components, if you looked at just all of the first components in a set of ordered pairs, we call that the domain. And if you took all of the elements in the second position in all of your ordered pairs, we call that the range. And in this first example, we're asked to determine the domain and range of the relation, and we can write those as sets. So the domain, in this case, would be a set containing the elements -3, 6, -4, and you see that -4 appears twice. But when we make our list of domain values, we're only going to list individual instances of any of those values. So even though there's duplication of some x values here, we're only going to list those once. And then let's check out the range. We'll express that as a set also. Those are our second elements. So we have a -3, a -9, a -6, and a +1. It's not necessary that those values appear in order. Often they would be if this were, if we were starting out with just a presentation of domain values or range values, and then we had to rebuild perhaps the relation. Maybe we would see them in order. But even typing them in online, it should not be necessary to order them. Similar process for determining the domain and range in number 2. In number 3, the presentation of the relation is a little bit different. We're seeing this as a table of values. And we'd like to write a list or a set of ordered pairs for this relation. So let's represent this as a set of ordered pairs, where the first one would be Bob L. The first element in that ordered pair is Bob L, and the second element, our range value, the corresponding range value would be 83. And then in our next ordered pair, Susan H, 83 also. Next ordered pair is Jim H, 76, and finally Bruce B, 96. And then make sure you close your set braces here, or your set brackets. So that would be a different way of presenting this relation. To write out the domain of this relation, we would put those values in the set, and then you would have Bob, comma, Susan, comma, Jim, comma, Bruce. And your range values would be the numbers that are associated with each of those names, 83 and 83. So we're only going to write the 83 once, 76 and 96. So interesting, we've seen some relations here that have a differing number of elements in the domain and the range, and that is perfectly okay. Another way that sometimes a relation is presented is like this. This is a mapping, and I would say that it's maybe even more common that the mapping would appear as something more like this, with some little boundaries around the domain and range values, but could show up either way. These are your domain values, these are the range values, and we're being asked to write this relation as a set of ordered pairs in number 4 here. So here's our set, and here's our first ordered pair. Now A, over here to the right, has an arrow pointing at the x, so I'm going to write A comma x. In my next ordered pair, I see that B is mapping to x. Next, I see that B also maps to y. And finally, C maps to Z. Again, your domain values, that would be a set containing A, B, C, and your range would be a set containing X, comma, Y, comma, Z. Very similar process that you would go through in number 5. We just have some different types of domain and range elements. These are actual words or names or species instead of just letters. And then in number 6, we see another presentation, a different way of presenting a relation. And here, these are being presented as not just ordered pairs, but these ordered pairs have been plotted already. And we're being asked to first write the relation as a set of ordered pairs. So we would put our set braces and then keep track so that you don't have any duplicates. This first point appears at -7, -4. So as an ordered pair, -7, -4, comma, and then the coordinates of your next point. That looks like -5, 6. Next is 2, 0. 4, 3. And finally, 6, -3. Not difficult stuff, but remember that this is the first section in a new chapter, and so we're starting with these basic building blocks, and I promise you we're going to be building on top of these ideas. Find the domain and the range. So the domain, again, you would present it as a set just of the x values, -7, -5, 2, 4, 6, and your range values also as a set. Oop, that last one got a little out of control. That's a little rough. -4, 6, 0, 3, -3. And all of the entries should be separated by a comma. So we've gone from actual, literally sets of ordered pairs, and then we've seen some mappings, and then we saw points that were plotted. And now in number 7, we're seeing what look like more traditional graphs. And we're still being asked to express the domain and the range of these relations. However, we're being asked to do that using interval notation. And interval notation will be the most efficient way to do this because, for example, when we look at this circle here, this circle has a lot of points on it, not just at the whole numbers or the integer values, but there's all of these points. There are infinitely many points going around this circle. And somehow we're supposed to make a list of all of the x values. That's the domain. And then we're also supposed to make a list of all of those points' range values or y values, and that'll be the range. And the way that we include all infinitely many of those points is to use interval notation. So when I look at this graph, I ask myself, how far to the left does my graph go? If I look at the leftmost point on this graph, what is its x-coordinate? And it looks like -5. And then consistently there are points going through here that have all of these different x values. All of them, all of them, all of them. If I drew enough lines, this would be totally solid. All right, there's infinitely many points. And then these points continue over here to the right, and they have all of these x values, all the way up to an x value of +5. And so for my domain, I'm going to say that if I made a list of all of those x values, the lowest one would be -5, the highest one would be +5, and everything in between, all of the x values between negative and +5, including negative and +5, which is why I have used these square brackets right here instead of using a parenthesis. And what about my range values? How low does my graph go? This comes all the way down to a point that does have a y value of -5, and all the way up to a point that does have a y value of +5. So our range values are going from -5, our y values are going from -5 up to +5, and everything in between. Can you find me a point that has a y value of -4.37? Absolutely. -4.37. Yep, there's one. Absolutely. Matter of fact, there's another one over here. What about +1.02964338? Absolutely. Find that y value, come over here. Yeah, absolutely. There's one of those. In fact, if you go to the left, there's one there too. So you can see that for any one of these y values in the range, we can find a point on our graph that has that point, or that has a point with that y coordinate. Now this one's different, and in fact, to make this most proper, there should be an arrow on the bottom of this graph indicating that this curve continues down and to the left, and it's getting wider going down and to the right. So we should have arrows on the bottoms of that curve. They're not always there, but this definitely looks like an upside down parabola, so you should think of it as such and assume. You shouldn't have to assume, but in this case, I'm making the assumption that this thing's going all the way down, and as it goes farther down, it's getting wider and wider. And again, the way that I like to ask myself the question in order to determine the domain and the range is, how far to the left does this graph go? How far to the left in the x direction? And the answer is, as it goes down, it keeps going, getting wider and wider to the left and to the right. So this thing's going to head off all the way to -infinity as it goes down and to the left. And as this branch, so to speak, continues going down, it's going to continue going out to the right, all the way out toward +infinity. So that's in the horizontal direction. What about vertically? What about my y values? From lowest to highest, and I always investigate from lowest to highest, I'm seeing that these arrows are pointing all the way down toward -infinity. And what about the highest y value? It looks like we're reaching a y value of +9, and I see that closed circle, that colored in dot right there at the top. That's telling me that we do actually reach a point with a y value of +9. And so when I'm writing out my range and I put my 9 here, I'm going to include that value of 9 by using the square bracket. So make sure that you put in your notes, if you need to, if you're not super comfortable with this idea, that the square bracket again has appeared here because we are reaching a point with a y value of +9. Infinity and -infinity, however, always take a parenthesis, or an open bracket, some of us call it. And then a couple of applied problems. Number 9 here is giving us a function p equals 1 plus d over 33, which gives the pressure, capital P, in atmospheres at a depth d feet in the sea. I won't sing. We're going under the sea though. And as you know from maybe diving down pretty deep into a swimming pool even, as you go down, your ears start to hurt, and that's because all that water is pushing down on you and it's trying to push into your ears. And so this function is telling us about the amount of pressure that's occurring as we go farther and farther down. And they want us to find the pressure at 35 feet. So 35 feet, obviously the unit of measure there is feet, which is a clue that that is a d value because d is measured in feet. So we'll take that value of 35 and plug it in here for d. So P is going to equal 1 plus 35 over 33. And you could solve this by typing it into a calculator. I punched it into mine. 35 divided by 33 was 1.06. Repeating, 1.060606. I put the bar over it to indicate that it repeats over and over again. If I add these together, I get 2.06 repeating. And the hope would be that you would be given some more specific instructions about rounding. So maybe you would just give your answer as 2.06 or 2.1 atmospheres. I guess it's lowercase. ATM. All right. And sometimes this equal sign, since it's an approximation, will appear as a wavy equal sign to indicate that this is actually an approximation of what came previously. So just be careful and watch out for those specific instructions about rounding. In number 10, I don't want to go through all of these. I won't write them out. I don't anticipate that you're going to be copying down this table necessarily. If you have the ability to print these notes and you want to be filling it in, let's talk through it. The one-day temperatures for 12 world cities, along with their latitudes, that's interesting, is shown in the table. And along with their latitudes. That's not true. These are not latitudes that are being shown in this table, I just realized. These are temperatures. So on one particular day, the same day, 12 different cities around the world, their temperature was measured and recorded. And for example, in Oslo, the temperature was 30 degrees. In Seattle, Washington, the temperature was 57 degrees. And all these temperatures occurred on the same day. Okay, so what is the range element, part A asks us, corresponding to Paris? So we're going to assume that the names of these cities are our domain values, the temperatures are our range values, and we want the range value corresponding to Paris, and I think it's pretty clear that that is 61 degrees. What is the range element corresponding to Egypt? So find Egypt in the domain. Oh, there it is, Cairo, Egypt. Interesting that in part B, they're giving us the name of the country. In part A, they gave us the name of a city. So Egypt, Cairo matches up to 82 degrees. And then here we're going with a slightly different question. Which element in the domain corresponds to the least value in the range? It would be nice if all of these range values were organized in increasing order. They're not, so we have to look carefully, and I see that 30 degrees right at the top of that list is the lowest temperature. It's the lowest value in the range, and it corresponds to Oslo, Norway. So I wouldn't normally draw an arrow mapping it back to Oslo because we always map from domain to the range, but just realize that those two correspond. So Oslo, Norway. Part D asks us to complete the ordered pair. They're giving us a y value, a range value of 54 degrees. And thankfully, all of these range values are only occurring once, so I can go up into my range values, find the 54, and see that it has a corresponding domain value of Vancouver, Canada. So we would write Vancouver, Canada in here. Completing the next ordered pair, sort of going the other direction, they're giving us Manila, which is in the Philippines, as a domain value, which corresponds to a range value of 93. And then just very broadly, we're being asked for the domain of the relation, and in a set, and it would have to be a much wider set than this, we would list all of those city and country values. Now that would be a little bit tricky because each of these domain values has a comma in it, which I would say is not typical. So I'm not honestly entirely sure what the protocol would be if you had commas occurring in your domain values. I will have to investigate that. I'm not sure about that. I don't see that very frequently, and in the vast majority of the work that we're going to do, we're going to be working with X and Y values that are numerical values. But I'll look into that and see what happens when we've got domain values that have commas in them. And of course, the very last question in this section has stumped me, what to do about those commas. I'll look into that. If I can figure out a great answer for you, I will put it in the notes. Otherwise, I look forward to seeing you in section 2. Thanks so much.